Okay, thank you, Ashar, and thank you all for being here. So the talk will be on network calculus. I've always been done network calculus, and I continue to be very stubborn and keep doing it. And there are not many people doing it, but I'm one of those very few. Okay, so for a long time, I was told a story that computer scientists, they give up reading queuing theory books after the first chapter, myself included. And the reason is that beyond the MM1 model, the mathematics, they just get too complicated in a way for us. Now, network calculus is just an alternative to the classical queuing theory and has been designed and is being designed with the goal, or with the computer scientists and engineers as the primary audience. So if I may say so, the network calculus is just queuing theory for dummies. I hope I'm not insulting anyone.
Don't say it to CS China.
No, but that's what it is. I'm a frank person. Yeah, so now after more than 20 years of research in this, I'm not sure how successful have we been, in the sense that network calculus is being regarded with a lot of skepticism from many communities, and for good reasons. And the primary reason is that, so unlike queuing theory, which goes for exact results on queuing metrics, network calculus is more relaxed somehow, so it goes for bounds. So mathematically, there is more freedom to compute these bounds. So whenever something is very difficult, we just put an inequality, and we simplify the problem. And for 20 years, these inequalities, somehow they just went on, and they were quite loose. And some people, they knew about that, but most of the people were just, they didn't acknowledge, and they kept doing it, myself included. So in this talk, I'll reveal that these bounds that network calculus produces are actually very loose, to the point that they are just simply unusable. The talk won't stop there. I'll just show how to improve the bounds to the point of making them very tight. But as there is no free lunch, or there is nothing for free, there is a price for that. And the price is that the mathematics itself, it has to get more involved, so more difficult. So along the talk, I'll first briefly introduce the general problem that we are looking at, and then make some historical remarks on the classical queuing theory, and then highlight the main concepts in network calculus, how it goes, and then get to this lingering issue of bounds tightness and show how to make the improvements. So broadly speaking, we are looking at systems which consist of some resources. There is some input and some output, and what we care for is the performance of these systems. Now, what makes the problem very difficult is that these resources are finite. So whenever there is more load than resources, automatically there is either loss or some delay in the system. There are multiple ways to formulate the performance analysis, and one way is as a resource allocation problem. That is, given the load and some performance target, what are the resources needed in order to meet that performance target? Now, this problem is very old, and the reason that we keep looking at it is that it reincarnates itself in many ways. And to give you a concrete example, let me first give you some cold facts on data centers, just some example. So data centers are expected to consume more than 10% energy by 2020. They consume a lot of, or they produce a lot of these carbon emissions. The other fact that I want to emphasize is that the electrical grid is sized for the peak energy demand. That means that in practice, there is a gap roughly by a factor of 2 between the energy supply and the energy demand. So by the way, that plot is from the state of Ontario, and some people recognize it. Now, as a concrete example of a resource allocation problem, let's consider powering up data centers from renewable sources. Now, renewable sources are highly fluctuating. And in order to to absorb these high fluctuations, one good idea or seemingly good idea is to use a battery to absorb these fluctuations. The idea is very simple, like a knight, just fill up the battery and use it whenever it's necessary. Now, there are two ways of approaching this problem, like using an exact approach, meaning we'll get the exact battery size needed in order to absorb these fluctuations and reduce this gap between the energy supply and the demand. Or the other approach is just to use these inequalities and get bounds. Now, if the bounds are very bad, that means that we'll overly provision this battery. And the problem is that, or the economical problem is that the cost to store an energy unit is much higher by a factor of 3, I guess, than the cost to produce that energy unit. So we really have to get this problem right. 4,000. It's very high. So if we overly dimension this battery, it's just, the result itself is just bogus. Now, mathematically, the problem is very difficult because the energy from these renewables is highly fluctuating. Yeah, so what kind of model can we fit to these traces? So here is a solar trace, yeah, as a function of time, and here is from wind. And there are like 30 traces in each plot. Now let me break down the system, this general system, and let me break down in components, and roughly I break it down into a server and a queue. Yeah, like remember that the amount of resources are finite. So the input, so what we like to analyze the system, we need the input, so we need some kind of statistical description, and then we need other factors like the queue size, the scheduling, and what we get in the end, we get some performance results. For instance, what's the battery size such that the probability that we meet the load and the demand with high probability, we meet the load with demand with high probability. To make some historical remarks, so queuing theory was invented by Erlang, like roughly a century ago. And here, roughly, he looked at the following problem. So there is some remote village, like Waterloo. And so what's the problem? Like the resource allocation problem is, so given these guys who have phones, how many telephone lines do I need to connect to Toronto such that the probability of getting a busy tone is very low? So that's the problem. Now to formalize that in a queuing framework, so we have the customers, and there is like some inter-arrival time, and there is some call duration. So Erlang's main contributions, it's two contributions. One is he came up with the exponential distributions for both the inter-arrival times and the call durations. And then the famous blocking probability formula, which is still being used nowadays. And the main result of, or the main manifestation of this blocking probability formula is that it yields the so-called multiplexing gain, or economies of scale. That means that the number of lines which are needed in this scenario is much smaller than the number of customers. Now to jump in time to the when internet was emerging, so queuing theory at that time was quite a mature theory, and it was actually instrumental to for the implementation of the packet switching technology in the internet. That is, all flows, they share the available bandwidth by interleaving these packets. Yeah, so that was fundamentally different than the circuit switching technology. And the advantage of this packet switching technology, again, the manifestation of it, is the statistical multiplexing gain. The bandwidth needed to support service for n flows is much larger than n times whatever. Yeah, so with circuit switching, we would have equality here. Now, the problem with this packet switching technology is that there is queuing now. Yeah, so it's much more difficult to analyze it. And I forgot to mention on the previous slide, so here, like in this circuit switching setting, we see that somehow queuing theory, ironically, was invented by looking at a system with no queue. Yeah? But now we really have these queues in, like in these routers, the buffers. So to model the internet traffic, the way that it was done is just by simply following the models from the telephone network. So the packet arrivals, Poisson process, the packet sizes are exponential. Now to analyze a network of these, let's say, routers, one had to make the rather awkward assumption, artificial assumptions, that packets change their sizes in the network. Yeah, so physically that's just impossible. But again, in order to analyze a network of queues, one had to make this assumption that the packet sizes are independently regenerated. Numerically, that assumption was justified. Yeah, so the packets, they just change their sizes. Numerically, the assumption was justified. However, we showed that this assumption leads to incorrect scalings of end-to-end results. So by making the assumption, the end-to-end delays, let's say, they would scale linearly with the number of nodes. However, in reality, we showed there's a big theta, yeah, lower and upper bound. There is an additional logarithmic factor. In practice, it really doesn't matter. So this is just the theoretical result. Yeah?
What do you mean by numerically justified?
Meaning, it does if you do make that assumption, the exact results differ from the results with the assumption by a small factor, especially when there are enough, like 4, 5, 10 nodes in the network and sufficiently high traffic load, it just doesn't matter. The results are almost as exact. So that's Kleinrock PhD thesis. So he has, that's the assumption is called the Kleinrock independent assumption. And he has done that in order to apply the Jackson network result. Yeah, so again, from the 60s to roughly the 90s, internet traffic was modeled as Poisson. Now in the 90s, there was this discovery that the internet traffic is fundamentally different than the Poisson traffic. And the convincing argument roughly was this picture. So here what I show, I have a trace, and let's look at the bottom plot. I just put this data in bins of 1,000, like in bins of 1 second. And here I plot the data rate as a function of this bin number. And then what I do, I take a fraction of this data trace here, and then I do the same with 1,000 bins, but for 100 milliseconds bin size. And I see now that over like 3 time scales, the data remains bursty. Yeah? So it doesn't sort of like levels out. So that's the sort of the intuitive proof that this internet traffic is fundamentally different than the Poisson. So what that means is that if one applies this Poisson model, the results are just bogus, yeah, completely misleading. And in response to that, there has been a lot of effort to come up with more sophisticated mathematical models, and they are all great results. Most of them are asymptotic results. However, the problem now, from our perspective, is that the mathematics is just very, very difficult. So not even the first chapter, it's sort of possible like to go through. Now, let me take one of these Belcourt traces, and let's look at the following problem, like a resource allocation problem. So I take a trace. I have n bins, like 1,000 bins, the bin size, and roughly the trace is, the data rate is very small, so this is data from the 90s. And now I push this trace, the Belcourt trace, I push it through a link such that the utilization is 75%. Yeah, so this capacity here is a little bit higher than 5.2. And I asked the question, what is the delay of these packets through this link? And there are many ways to do it. One way, the immediate way, is just to simulate O of n time and just get it over with. The second way is to fit a traffic model, like to that trace, and just run some results. Yeah, the immediate question, of course, is which model to use for that. And using the Poisson model, is just the results will just be bogus. Yeah, completely misleading. Now, let me show you how network calculus. So I didn't talk anything until now about network calculus. I'll just highlight roughly how it works. So remember that I have this data trace, and let me denote A of kn, the cumulative variables in the bins from k to n. And then I build the so-called empirical envelope, which pretty much E of k is just the maximum of bits in any consecutive k bins. So what I do now, I plot this empirical envelope as a function of number of bins. And now I also plot the service line. So C, I know C, yeah? C is like 7 kilobits or something. Now the delay that I get, the delay would be the maximum distance between these two curves. That's the delay, the worst case delay. Now the time to get that is O of n squared, and that comes from the fact that I have to compute these maximums, and then plus O of n to compute this maximum distance. Yeah, there is another alternative to it. So having this empirical envelope, now what I do, I draw a tangent to that. It's up to me, it just has to be a tangent. And then I draw this service line, again, this is unknown, that's CT. Now the delay would be the maximum distance between this tangent and the service line. And the time is as before, plus this O of 1, because the green and the blue are just functions, so I can immediately get that maximum. Now, why would we do that as opposed to simulations? Why would we do something that takes O of n squared as opposed to O of n? And the reason is that we can reuse these traffic models. So once we have the traffic model, we can just keep applying it. And in the end, we only need O of 1. Yeah, so we can apply it in all kinds of queuing scenarios consisting of if we want to aggregate, if we want to do scheduling, and so on. Yeah, in the end, the delay boils down to O of 1 operation. Now, the drawback for that is that these delays are just bounds here. Yeah, it's just worst case bounds. We have no idea if, like in reality, if they are attained. So, in a nutshell, so network calculus looks at this system performance analysis by roughly putting bounds. Yeah, so it bounds the load with these envelopes, and also it bounds the service. And inevitably, the performance results, they have to come up. And as I said, yeah, and then use inequalities whenever things are difficult. Inevitably, the results, the performance results will show up in terms of bounds. Now, why do we do that? Yeah, and the reason is that unlike the classical queuing theory, we can work with very broad classes of loads and resources, and somehow the mathematics is much more intuitive than the mathematics in the classical queuing theory. Yeah, so intuitively, it's much easier to work with these envelopes, just lines, yeah, than just to work with stochastic processes. So just briefly to talk about these envelopes in a little bit more detail. So remember this empirical envelope, just the maximum in any consecutive k bits. So this red line would be the cumulative arrival process from that trace. This would be the empirical envelope. And now this deterministic envelope is just a line. It's a tangent. So that's called the leaky bucket envelope. R will be the rate, and B would be the burst, the initial burst. Yeah, so what's important to observe is that, so the trace and also this envelope, these are random processes, whereas the deterministic envelope is just a deterministic function. So what happens is just we bound a stochastic process by a deterministic quantity. It's very trivial somehow. Now, the reason why it works is the following. If we look at a queuing system with one arrival and then some capacity, now we know from queuing theory there is a classical equation that the backlog at time n is just some function of the arrivals and the capacity. And now because we have a bound, we have a deterministic bound on this stochastic process here, it's just very easy to compute this backlog. Yeah, so A of kn is just the random process is bounded by a deterministic function, so we just put that bound there and just get it over with. Yeah, the price again is that we obtain a bound on the backlog and we don't have an exact result. So that's deterministic network calculus. And you can think that these bounds, they have to be loose somehow. And for that reason, to improve the bounds, the sort of the immediate idea is to transpose all this theory like in a probabilistic space. And roughly, the idea is to get the deterministic envelope and allow for some violations. Now, so what we do, we just push it down a little bit. We have some violations epsilon. So roughly, a stochastic envelope now would be, again, a deterministic function, but that which satisfies like a stochastic bound. The probability that we violate that envelope by more than some quantity, we can bound it. And in this framework now, we can take advantage of laws of large numbers and so on. So somehow, conceivably, the bounds, they have to get better. So that was modeling arrivals. Yeah, envelope, deterministic, and stochastic envelopes. Now, in terms of service modeling, the idea is the following. So let's look at a simple queuing system with one arrival, some server capacity C, and again, we have this classical equation in queuing theory. The departure process is just some expression of the arrivals and the capacity. And let's now make an analogy with linear and time invariant systems. So what we have here, we have a signal, which is just a sequence, and we have the output, another signal. Now, if the system is LTI, linear and time invariant, we know that there exists this impulse response such that for every arrival, for every input A, we can uniquely determine the output. So the output would be the convolution of the input and this impulse response. So the analogy should be quite clear at this point. In the queuing system and in this LTI system. Yeah, for every input, like here and here, we can determine the departure. The difference is that, or the fundamental difference is the algebra in which of these operations. So here we have the classical convolution, the sum or the integral of the product. Here we have the mean plus. Yeah, so we change the sum by a mean and the product here by a plus. So that was a very simple queuing system, only one flow. But in general, I mentioned that in network calculus, the reason we do this is that we do scheduling. So in scheduling, we are interested in the performance of a flow A that goes through a server with some like time-varying capacity, let's say, and there is also some cross-traffic there, and there is some scheduling. And the question is, what's the performance of this single flow, of the blue flow? Yeah, now, to make that analogy, this system is definitely not mean plus linear. Yeah, and at this point, again, there is a lot of freedom. We work with bounds. So what network calculus does is transforms the system into something which is somewhat looking mean plus linear. So pretty much what happens is that one takes or one encodes the information about this cross traffic, the scheduling, and the server into some stochastic process S, such that for every arrival process A, the departure process is bounded by this mean plus convolution, yeah, for all A. And that's what happens. Yeah, so one just encodes the scheduling, the cross traffic in this stochastic process, such that one has this bound. And with that, one can derive delayed backlog bounds right away. So that's one feature of network calculus, this encoding. And of course, there is the price. The price is this inequality, which can be very loose. The other immediate advantage of this encoding or of this constructing this service process is that they can convolve over a multi-hop network. Yeah, so if one has a flow A and somehow is able to construct the service processes, they nicely convolve in this mean plus algebra. And one can immediately get end-to-end results without caring if one has Poisson arrivals here or not.
Except for flow through with no loop back, right?
Yeah, it's just feed forward. At this point, everything is feed forward. Okay, so that's the state of the art roughly in network calculus. And as I mentioned, there is a lot of mistrust out there because these bounds are not tight. And they are not tight. Ironically, the deterministic bounds, they are tight. They are tight, but they never happen. Because if you think that you have like 1,000 flows, those bursts never happen at the same time. Although in principle, it's possible. And the INSERV architecture of the internet, which is the architecture to provide performance guaranteed, the INSERV was based on this network calculus. And for that reason, because these bounds they never happen, the INSERV, or if one were to use INSERV to dimension a network, would be a disaster. And for that reason, INSERV is not being deployed. Now, in contrast, the stochastic network calculus bounds, in principle, they could be tight, but only if the right probabilistic methods are used, which has not been the case for 20 years. And now, before I go into that, so before I go into this detail here, let me just briefly contrast the deterministic and the stochastic network calculus bounds. So here again, I look at the resource allocation problem. There is a C missing there. So I have n flows, and the question that I ask, what's the capacity needed such that the delay for any packet here is less than 1? And I think there are some equations are missing. Anyway, so all these flows, they are bounded by a deterministic envelope, like rho t plus sigma. Now, if I look at so if I want to solve the problem in network calculus, what I do, I build the envelope for the aggregate. Now, this envelope would have a burst of n, the number of flows, n sigma. So that's what I have here, O of n. And that's the envelope. Now, I want the delay of 1. So I reverse engineer what I told you earlier, how to compute the delay. I want a delay of 1. So now, what would be the the capacity line or the service line to meet that? Yeah. So that will give me the C. The capacity would be O of n. N is the number of flows. Now, if I try to solve the same problem with stochastic network calculus by inside the theory or by speculating the laws of large numbers, remember now we work like in a probabilistic space, the burst or the stochastic burst is just O of square root of n. And if I apply the same method to compute that capacity, the C would be O of square root of n. Yeah, so you see that INSERV roughly would give you a complete overestimation of the actual capacity needed. Now, I found the following statement by Kingman. So Kingman he gave the keynote, I think, at the Erlang, it's like a famous talk in 2009. So I won't read everything, I'll just say this. So he said the following: why do we insist on regarding the arrival times as random variables? Yeah, so one may reflect on that. I have no idea what he wanted to say, yeah. But pretty much he said that the way that we do queuing theory is very, very, maybe not the right way. So Kingman is one of the main queuing theory guys. Now, from my point of view, I ask myself, do we have the right models? Yeah, so in network calculus, we do not work with random variables. We have these envelopes. Yeah, we have these stochastic envelopes. Yeah, the probability that we violate the envelope, it's something. So is that the right model? And the fact is that it's not the right model. For the very simple case, because it doesn't capture the correlations within a flow. Yeah, so you see the K and N here are just outside this. And for that very reason, the correlations within the flow, they are not captured. Moreover, when one tries to derive performance results based on these envelopes, one is forced to use the so-called union bound or the Boole's inequality. And this inequality is unfortunately very loose unless these accents here are ID. Yeah, so this in principle for Poisson it works, or it's reasonably tight, but whenever one has a bursted traffic, it just, it doesn't work, or it doesn't produce anything meaningful. So how to account for those correlations, or how to come up with a new model? And the idea that we had is just to use martingales. So here is super martingales. So roughly the martingale is super martingale is a process such that the expected increment, yeah, so we have a time n, the expected increment at time n, given the history, is negative. The martingale would be equal to 0. And the first thing to observe is that there is an analogy with queuing system. In queuing system, the expected buffer change, it's also negative. So this is like a conceptual sort of like analogy between the two. And this comes from the stability condition. So that's the first thing. Now what we did was just, in order like to introduce these martingales as sort of as a model to capture these correlations in the traffic. So what we actually did is to construct these martingales, but not for the arrival process itself, but for a transformation of the whole queuing system. So yeah, the definition for some theta and some h is a function. The flow A admits a h, this function theta, C would be the capacitive martingale envelope. If this process now, Mn, so what I have here is h, that function of the instantaneous arrival at time n, and this exponential transform of the queuing system. Yeah, so I have the arrival A, and I have the capacity. So this is a martingale envelope if this process is just, it's completely unintuitive, but I'll give an example to make it clear. So C will be the allocated capacity to this flow, and then theta, somehow it's the exponential decay rate, whereas H would really capture the correlation structure in the arrival process A. Some immediate results, yeah, one can change or one can switch between different thetas just using the Janssen inequality. Now there are two very attractive features of, like immediate features of these martingale envelopes, in the sense that one can address basic queuing operations like multiplexing and scheduling by through operations on these martingales. So one, if takes the multiplexing operation, yeah, when we multiplex two flows, so two flows A1 and A2, if they admit like the martingale envelopes to the same theta, then the aggregate admits another martingale envelope just directly. What changes is that one needs like some convolution here for the new function h. Yeah, it's some technical result. And the reason we have that is just because the two independent martingales, I multiply them, the result is also a martingale. The second operation, or the main one, the scheduling, that's the tough one. So remember, we look at what we hear is the performance of a single flow when pushed through some queuing with cross traffic and scheduling and so on. So now the idea is the following. So if I have a martingale envelope for my flow A and another one, MC, C comes from cross traffic, yeah, for the cross traffic, then for some switching time K, yeah, so K is just a number, the following process is also a martingale. So what happens here, I just take until this switching time K, I take this martingale, and then I take the two and I multiply them. Again, it looks unintuitive, but unfortunately that's the way it is. Now the key parameter here is this switching parameter K. And K depends on the scheduling.
Just a question to clarify. So what property does your martingale envelope have to satisfy? So, no, but other than that, what's the relationship to the stochastic process that characterizes the system? So is it pointwise greater than the stochastic process at all times? Or
Yeah, it's AS.
almost surely greater than
Yeah.
Okay, and it's a
So the transform. Yeah. So to give you concretely to show how this K how this switching parameter k works. So let's say that we want to estimate the delay bound for this, like through traffic, for the blue flow. Now, if we have FIFO scheduling, that k is simply 0. And that's because, like in FIFO, it's just the packets from the through and the cross flow, they compete at the same time scale somehow when they arrive. Now, in static priority, this switching time would be just d. And that's because somehow, like what happens more than d in the past, it doesn't matter. And the cross flow has priority over this blue flow that we care for. Whereas for EDF, so in EDF, we assign these relative deadlines, D1 star and D2 star. And let's say that D1 star is greater than D2 star. Then this switching parameter between the two martingales is just that expression. And then, by the way, this result comes from the work of Yashar, of his way of encoding EDF into this service process. So let me give you like a quick example of processes now. The simplest possible one, so processes with sort of correlations. So we look at on-off processes, discrete time. Yeah, so we have like a two-state Markov chain, AK, we have P and Q, these are the transitions, and we have the stationary distribution and the arrival process. So what we have the transition matrix T, and the key idea now is just I'm reusing ideas from Nick Duffield, is just to make a transform, like an exponential transform of this transition matrix by adding these exponentials on the last column. And from this matrix, I compute the spectral radius and the corresponding eigenvector. And now, if I can choose C, like the sort of the capacity and that theta, that exponential decay rate, such that the spectral radius at theta, yes, so the theta, like in this matrix, is that, then now this process is a martingale. Yeah, this is the result of Nick Duffield. So what I have here, that function h, yeah, that very weird function h. So remember that h is defined on the values of my arrival process. And my arrival process is either 0 or r. So h of 0 would be v0. So v here it's the eigenvector. Yeah, so h of 0 is v0 and h of r is v1. Yeah, so that's the result of Nick Duffield. It's actually like a fundamental result. And from what he told me, like it took him a long time to come up with this. It's beautiful. So now, so let's say that we have multiple of these flows, these on-off flows, and we want to get the delay for some of them. And in a scheduling system, or we have either FIFO, static priority, or EDF. Now, the classical way of doing it for 20 years in network calculus is just to apply the Boole's inequality. Yeah, keep doing it. Things are very nice, get exponential results. Like pretty much undergrad students can basically follow that. Now, the key observation now is that if this xn is a martingale, then one has another like inequality or a much sharper inequality to use, and that's the so-called Dub's inequality. Yeah, so instead of bounding this probability of a supremum, so this supremum, it comes from that equation of Lindley's. So instead of bounding that supremum by that sum, which is just very loose, a bound is simply the expected value at time 0 and then sigma minus 1. And one uses this Dub's inequality when sigma is like some exponential transform. Yeah, so using this Dub's inequality now, and in order to get our delays for the sort of this blue flow, we get the following results. And the critical observation here is that, so what we get like an exponential decay. So actually this theta that we get here is the same that we get with Boole's inequality. But what we get now, what we further get is this exponential decay factor, gamma power of n. And the critical thing is that this gamma is less than 1. So the more flows we have, the sharper these results are. And by the way, if one uses Boole inequality, this factor is always greater than 1. Yeah, so you can see the differences. Some numerical results. So here I have like 10 through flows and 10 cross flows. I'll give you the details. So what I plot here, I plot the violation probability as a function of the delay. Yeah, so delays from 0 to 50 milliseconds, or the probability of violating that. And the first thing, I have the simulations. So the simulations are like box plots that you see here. And then if I were to apply the network calculus, like people have done it for 20 years, I get this red line. So pretty much is something, a difference between 10 to minus 2 and 10 to minus 4. Huge gap. Whereas if I apply this Dubs inequality with these martingales, I simply get, I cannot get better than that roughly. So that's for FIFO. For static probability, nothing changes. And the plot that I like the most, it's for EDF. So EDF, I have these relative deadlines are like 10 and 1. So you see that we even get the band here. Yeah? So 10 and 1 here would be 9. So that's why there is that band there at 9, because the relative delays are 10 and 1. So that's pretty much it. So to conclude, like with these new systems that we are trying to address, the randomness, it sort of like gets more and more sophisticated. So trying to apply the traditional tools, can be very misleading. Stochastic network calculus is just an alternative. It's mathematically easier, yeah, like Q theory for dummies. It can deliver more in the sense like more traffic classes, more scheduling, multi-node, and so on. There is the price of this bounded approach. And then with respect to this tightness, yeah, the deterministic network calculus, they are tight. Ironically, they are tight, but they are completely unuseful. And then the classical bounds, we show that are loose by, like an orders of magnitude of, actually arbitrary orders of magnitude. One can improve them, but again, like one really has to get like a grip on these arrival processes. There is no other way. Yeah. And that concludes my talk. Thank you.
So for your martingale bounds on the arrival process, what kind of arrival processes can you fit them to? I mean, you showed them for a simple two-state Markov, but are you able to do the kind of the fitting process for more sophisticated arrival?
Yeah, we did it for pretty much every Markov arrival process. Even autoregressive processes, which is again, autoregressive is also Markov, but because of the structure of the autoregressive process, we can get like exact, like very clean results. The problem with these Markov processes is that the results, the final results, they are not closed form because one has to compute these eigenvalues. And it's just very difficult, or for the general Markov arrival process, one cannot come up with the expressions for these eigenvalues. So there is just numerically.
So you have numeric, so you've given a Markov arrival process model, you can transform it into this e to the theta,
yeah.
And then you can numerically compute the eigenvector.
Exactly.
And then you can find the bound based on that. And that pushes through for multiple states as well.
The problem with the multi-state, yeah, so that's only single state. We cannot build a martingale for multi-node. It's a very difficult problem because there is like a convolution in there, and we need stronger, we need like bivariate martingales in order, it's like a technical argument in there. In principle, it's possible, but we're working on it. That's the next obvious step.
Can you do for on-off processes with general on times?
Probably not. If you think of
techniques, of course there are other techniques to analyze these systems, but in general on times, I think the problem is that where you need a Markovianness is to create a martingale, right? The exponential martingale, and that's very hard to do. So, but of course, if you have a martingale, then Dubs inequality is far better than Boole's.
Yeah. The thing is, we looked at FBM, for instance. And there are martingales for FBM traffic, but honestly, I cannot do the math at this point because it's
FBM is not a martingale. It's not even a semi-martingale.
No, there are transforms of that with stochastic calculus.
No, but they approximate, but there is, but FBM is not. It's
No,
known
no,
not
no,
to be a
yeah,
martingale.
yes, but
Has no martingale structure.
yeah.
One of the assumptions that you have to make sure that there are martingales is that the backtalk at any time is independent of the arrival at that time.
No. There is no assumption.
You don't need it.
It's just a transform of the arrival process. It's just one has to do the right transform. And some people, yeah, it took them a long time, but they came up with like beautiful transforms. So it's just an encoding. Yeah, it's a very tricky encoding of the whole queuing process, not only the arrivals. One has to take the whole queuing process with the capacity and so on. Yeah. So I should also say, so I only give these talks like to computer scientists. Like I'm a computer scientist, and again, the goal is to have this theory available for computer scientists. Like to do all kinds of crazy stuff. Of course, these martingales, one has to sweat a little bit for that.
So maybe you can comment on, so you kind of said like once you move past the MM queuing models, you start getting into very complicated queuing models.
Yeah.
And I've done some work using GG, whatever.
Mm-hmm.
But then you kind of went into all this convolution and this other types of complicated math.
Mm-hmm.
So what is like the trade-off that you're gaining by using the network calculus by avoiding the GG models? Like what is the, I guess GG models also kind of target the same kind of problem.
Mm-hmm.
And they both seem to be complicated, but for different reasons.
Mm-hmm.
So I guess what is the trade-off there? Like when is one preferable to the other?
Well, like if you were to do like single node, just use queuing theory. Because the results, you have results almost for everything. Now here, what we want to do the multi-node. That's what we can do. Because in queuing theory, beyond the Poisson model, it simply mainly doesn't work. So here one can do multi-node for any arrival process. And one can do it with these Boolean inequalities. It's just completely useless currently, because they're just very loose. Yes? But one can get nice results, and I got results for heavy-tailed, self-similar, end-to-end, upper and lower bounds. They are loose by a factor of 100. And yet, nobody could do this. Nobody could get these results, like non-asymptotic results, using this Boolean inequality.
So the main benefit comes in when you have like a network of queues.
Network of queues and scheduling. So scheduling, in principle, one can construct this, or one can encode information about scheduling in these service processes. And that's very tough. And Yashar was able to do that for EDF, which it just comes like a very nice process, and then one can, in a way, it's like I also call network calculus as virtualized queuing theory. So we virtualize sort of the complexity of the queue in some very simple way. It's like in programming languages. We don't do assembling. Yeah, we do high-level programming languages. Yeah, we just hide all those complexities in these new operations. And that's what network calculus does. It hides the complexity in these sort of neat processes at the price, and there is the price.
Thank you.
Just one moment. When you multiplex a number of independent sources, right? Let's take on off. If one uses kind of network calculus ideas to get the input process, the kind of, you mentioned it's sort of these sigmas add,
Mm-hmm.
and the rows is the sum of the rows, right?
Mm-hmm.
Now we take the fact that they are actually independent, and so things are not going to align.
Mm-hmm.
Do we have a very direct result on multiplexing those sources using stochastic network calculus? I know CD, all these guys tried it, right? Using all this Ballard here. All of those guys are very weak, and mathematically,
Yeah, we actually for this, it's in my SICOM paper actually, that I use So right
Then
here.
you have to square root it.
So here I use a result of Massoulier, I think, of Massoulier, Laurent Massoulier,
Yeah, yeah.
because he did that for leaky buckets. So I just reused his result and get that, I mean, clean result, because there has been results like, you know, like hand waving, approximations, but this is here is like clean. Yeah, the square root of n, but it's not my result. I mean, mathematically, it's just, yeah, one of the French guys, he did that. Yeah, so it's not, I mean, network calculus is, again, like we reuse what's been there, like in probability. Sort of the network calculus, the problems are to do this encoding, sort of, right? And my feeling is that we as computer scientists, for us, sort of, it's easier to do that because we understand scheduling. And to do that encoding, we can do that. But the tough math problems, I mean, we just reuse, yeah, like Dubs inequality. Or the switching idea. The switching idea, I mean, there is the optional switching theorem. We can switch between these martingales. So I'm just reusing, yeah. Yeah.
Do you have any idea how lucid is to, how dependent it is to use rules of equality and increase the resolution of the summation? Like the union bound?
The unit? No, but it's very weak.
Union bound is very weak. It's just union bounds.
I mean, for IID, it's okay. And it's actually, there is a very good paper by Talagrand, who has some results on concentration inequalities. And he goes, I mean, that's another direction. But he points out that that's very weak. So stop using it.